All right, we're going to continue our discussion on 2.4, and we're going to continue on continuity. We talked about one-sided limits, and now what is continuity? Well, what is it? Well, what it is, regardless definition, continuity actually means the same word as continuous. All right, continuous. All right, it's saying it's continuous by a pre-calculus definition. It means that no breaks in a graph, all right? So no breaks, you can't lift up your pencil if you ever did a graph. Usually you talk about continuity when you talk about polynomial functions, all right? Polynomial functions. So if I were to graph a polynomial function, all right, like so, this is continuous, all right? This is what we would maybe consider a polynomial. This is a continuous function, all right? I'll just write like that, if we're going to call that f, all right? No breaks in the graph, none whatsoever. Now, that's great and that's grand. However, there is a more precise calculus definition that we talked about before, and that is this. Well, a function f of x is continuous at a point c if all three of the following conditions are true. And we already talked about some of these, all right? And actually, this will help us define continuity and when we solve things algebraically. Because a function f of x is continuous at c if all three of these things are true. Well, first off, the limit of f of x is equal to c, it has to exist. So how do you know if it exists? Well, if you can see this right here, the right side of the limit has to equal the left side of the limit. If that is true, then the limit is going to exist. That is what we know, all right? That's the definition of a limit. We also have to know that f of c exists. So there actually is a value at c, all right? There is actually a value at c. And so finally, what we have is the limit of f of x is equal to c. In order for this to be continuous, that has to equal f of c. And that's what we talked about. That is when we know things are continuous. That's if you're solving algebraically, we can use direct substitution, and that is when all things are good. So when can we apply this? Well, continuity, all right, by its definition, all right, we can have interior and exterior points. Now, this is where we have one-sided limits come in. Interior points, if a limit of f of x equal to c equals f of c, that means any value right here. So if I put a c value here, and this is a open interval, so c is at any point on this interval from a to b, all right? Open means it does not equal that, okay? So open interval, this is what we call an open interval, all right? Open interval basically means that c, all right, is going to be between a and b, all right, and it does not equal. So if I take c, c can be any value, all right, right here, and I move it around from a to b, and as long as there is a limit and the value equal each other, which all these do, there's no holes or gaps, then it's going to be continuous. Now, the problem is that this is great for interior points right here. However, what about exterior points? Because technically, these exterior points, these endpoints, okay, exterior points are what we also refer to as endpoints. Technically, endpoints of a graph, if you looked at our other one, like the square root of x and whatnot, these at A and B do not have limits. Because on A, there's no left limit, and on B, there's no right limit. So are these continuous? And the answer is yes, they are continuous. If you have an exterior point, so you have a closed interval from A to B, we know, all right, that if you plugged in the limit, all right, as you approached A, oops, this should be A right here, all right, as you approach A, the endpoint from the right, and that equals f of a, that's going to be continuous. All right, so this would be the left endpoint. Okay, the left endpoint. Now, right here, in the same way, if you took our a value and you approached it from the left side, okay, left side. So I mean that I have to go this way. All right, this is actually going to be our B. All right, this would be our right endpoint. Okay. And that equaled the left value, all right, over here, then we would know that the endpoints are also going to be continuous. All right, so that makes sense. I don't think that's too difficult. All right, so what can we do? Well, right here, okay, we define continuity also by its discontinuity. And this is quick review. All right, you can write this down. I'm going to put the notes online, that kind of thing. So probably down if you want, but just really quick. So when do we have discontinuity? Well, we know when continuity, all right, occurs when direct substitution works out. But we also have removable discontinuity, which we talked about. Removable is when we have holes, okay? There's a hole right there, all right? And basically what we're saying is that the limit exists, But that limit at c, now if we say 1 is c, all right, that's going to equal, all right, can equal f of c. That it can equal f of c. Apologize for all the pop-ups, but what we have is then right here, this 1 is actually our c value, okay? So c in this case would equal 1, and then you can see x equal 1. So let's remove this continuity. The limit exists right here, which equals 2, all right? So if we do the limit as x approaches, all right, 1 right here for this function f of x, we would know the limit equals 2. However, f of 1, that equals negative 1. All right, so right here, we would know this is removal of this continuity. Also, when we use indeterminate form, all right, we plug a value in, that also is a keen sign that we have removed this continuity, which we talked about before. We also have our other where limits don't exist, okay? When we have non-removable, now everything that is not removable, where we have a holes, okay, is known as non-removable. So for example, when you have a jump in a graph, all right, so the limit doesn't exist, and you realize that the right side and the left side limit don't equal the same thing. So the limit right here, as x approaches 0 to the right of this function f of x, we'll say this is f of x again, all right, that equals 1, and the limit over here, as x approaches 0 to the left of f of x, we notice that equals negative 1. They do not equal, therefore we have a jump discontinuity. Over here, also vertical asymptotes. Vertical asymptotes, limit doesn't exist. And as you approach the c value, you go to positive or negative infinity. Positive, negative infinity. Essentially, they are not numbers, so it does not exist. But we could say where they do approach. So, for example, we would say the limit as x approaches 0 to the right, all right, to the right of this function f, all right, is going to infinity. And we would also say the limit, all right, as x approaches 0 to the left of f would be going to infinity as well, all right, and therefore the limit doesn't exist, all right. Direct substitution, key thing for this, direct substitution is when you plug in a value here, you'll get a number over 0, a number over 0. This is actually the function f is equal 1 over x squared. That means if I plug in our c value, all right, our c value right here, which is 0, we notice that we have f of 0 is 1 over 0. That tells us we have a vertical asymptote at c. Vertical asymptote. So number over 0, key thing to look for. We're going to talk about that more in the next lesson. And then obviously oscillation. You don't see this very often, but the limit doesn't exist, the right value doesn't exist, and the left value doesn't exist. They don't approach a single value, and you see the good old barcode. All right, well, let's try applying this stuff. All right, here we go. Use the graph below and find values, if any, at which f is not continuous. All right, so we're looking for where this is not continuous. So we're looking for where the limit at a value doesn't equal the actual value function. Right here, it appears we have a big old gap right there, and this is going to be at 1. All right, so where is x value? Well, it appears at 1. There is some discontinuity, okay? Which of the discontinuity is removable? Well, there is no not removable discontinuity because there's no holes, all right? The limit right here at 1 is vertical, so describe the interval on which the function is continuous. So we would say this is continuous, all right? It appears from negative infinity, all right, open interval, to 1, and then we would do a little unit because there's a big gap here, and then from 1, all right, 1 right there, going to infinity, and so the interval, all right, we would say that right there. So negative 1 to 1 and 1 to infinity, that would be the interval where this function is continuous. All right. It's very similar to domain, all right, very similar to domain, all right. Right here, use the graph below to find x values if the function is not continuous. So where is this not continuous? Well, right, endpoint continuous, all right, limit equals to value. Right here, big jump right there. So when x equals 1 again, and if you want to pause this before I go through the answers, that would be good. Try it out yourself. Right here, any continuity right here. Follow this graph, big old hole right there. Follow through, so also at 2, so those 2 values. Which of the discontinuities are removable? Well, this is a jump. This is a jump right here. This is the limit equals the value of the limit exists, but doesn't equal the value of the function. So we would say x equaling 2 is removable because the limit as x approaches 2, all right, and we'll call this f, all right, of f of x, that one equals 1, but that does not equal f of 2, which in case equals 2. All right, so right here, when x equals 2, that is where our removable discontinuity is. This one right here is a jump discontinuity. That's a jump. All right, jump discontinuity, and we call that non-removable. Non-removable. Basically, anything other than removable is non-removable. All right, we would say this is a jump discontinuity. Describe the interval where this function is continuous. Well, we have a closed interval. So at -1, it's an endpoint. We start at -1, so always start from the left to right. So whenever you're doing this, start left, right at left, right left to right, right left to right. So whenever you're solving this, we're left to right. So -1 is our farthest left value. Keep on going. Well, it's not continuous at 1. So we'd say, all right, comma to 1. That's going to be a closed interval because it's not continuous there at 1. We're going to do a union. Now we're going to start up at 1 again, and we keep on going down. So where it's continuous, well, it's not continuous at 2. So we go comma. Comma means going to 2, close that interval. And then we're going to do another union right there. And then we're going to go from 2 to 3, 2 to 3. So 2 to 3. Oops, and it's 3. 3 is closed, and it is the limit. So actually, this would be a closed interval right there. Closed, that's a bracket. All right, so that equals. So these are open, these are closed, and that would be our statement. All right, cool. Let's try some other. All right, how do you algebraically determine whether a function is continuous or not? All right, well, we did some graphs. So now how do you do this algebraically? Okay, algebraically. Well, there are some key things you're going to look at, and it's pretty easy. If you did domain, what we did in previous ones, and if you look at some other previous videos, what you basically look for is where undefined values are. And where do you find undefined value? Well, first, find the function where the function is discontinuous, identify the type. So check the denominator. It can't be 0, right? The denominator cannot be 0. Wherever the denominator is 0, that means we have undefined values, okay? An undefined value. Undefined values are discontinuity. All right, are discontinuity. I didn't say what type, but they are discontinuity. So any undefined value is discontinuity. The other one is you need to check the potential breaks in a piecewise function. They have to have the same value. Where you check those breaks, we'll talk about those in just a second. So let's go through a couple of those right now. So first off, find the values at which the function is not continuous. Well, right here in our function, all right, we don't have the graph, but if I just do this algebraically, I'm going to look at the denominator, okay? And you look at the denominator, and you're going to set that equal to 0. So right here, x squared minus x, set that equal to 0. We factor this. I'm going to move this over here. I have a little bit more room. All right. And what you notice is that you can factor out an x, and then we have x minus 1. And so essentially, what can x? Well, x, when the denominator equals 0, is going to be at 0 and 1. 0 and 1. Now, which of these discontinuities are removable? Well, now when you write this out, to figure out the removable discontinuity, if you recall, removable is where we have values where you get 0 over 0, indeterminate form. In order to get 0 over 0, you need to have a common factor in the numerator and denominator. So when you write this, factor the denominator or the numerator and look to see if there's any common factors. And what we see is when we factor this out, we notice that yes, this and this would cancel out and are common factors. Therefore, of these values that are not continuous, x equaling 0, where that makes it 0, is our removable discontinuity. So x equaling 0, because it's a common factor, numerator denominator right there, okay, that, my friends, is our removable discontinuity. That's our removable discontinuity. Describe the intervals on which the function is continuous. Well, right here, it's like our domain. This is going to be, well, where we start. Well, there's no endpoints that I know of. Okay, there's not a square root that would do that. So it's going to start at negative infinity. Remember, always go from left to right. And the farthest left value is negative infinity, open interval. And we're going to go to our next value, which would be 0. We're going to label that in. It's going to be open interval because it's not continuous there. Then we're going to go from 0 to the next value, which in this case we have 1. Then we're going to go right here, and then from 1 to infinity, and that would be our interval. All right, and that goes through and look at our 2 discontinuous values. Well, let's try another one. All right, find the values at which the function is not continuous. Well, right here, look at the denominator. Denominator cannot be 0, so it'd be x minus 7 equals 0. Why do I keep on putting it there? All right, put that right there. And so what do we notice? Yes, when x equals 7, all right, when x equals 7, that is where we have our discontinuity. All right, now, which of these functions removable? Well, you have to know something about this function. All right, you see that we have this canceled out. Look, there is an absolute value here. Now, normally, if you have a common factor, all right, you would say, okay, that's a whole. But if you graph this, all right, and this is a very, very common one. They originate from graphs like this, the absolute value of x over x. We did one similar to that. That's where we have discontinuity. But when we have this, we have 7 right here. And what happens is that we have an open circle there. This is going to equal 1. And down here, this is going to be negative 1. An interval right there. And we see right here, because of the absolute value, any value that's positive will stay positive. But as soon as the denominator becomes negative, this stays positive and therefore makes negative 1. So is this removable? No, this is a jump. All right, when x equals 7, that's a jump discontinuity. That's non-removable. It's non-removable. All right, and so right here, there is none. Okay, if not, well, what is it? X equals 7, that's a jump, that's non-removable. That's our explanation right here. That's our explanation. All right, and so now let's just define where this is continuous. All right, what's continuous? Remember, going from left to right. Sorry, and I'm always writing an angle, but that's how it works right now. All right, so where we start at negative infinity, open interval, going to our discontinuity, which is 7. Doesn't equal that, because obviously it's not continuous there. We're going to union right there, and we're going from 7 to infinity, and there we have it. All right, cool. We got another one. All right, one more. All right, and let's check this out. Find the values at which the function f is continuous or not continuous. Now, when you have a piecewise graph, this is where I said you have to look out. All right, take a look out. Right here, where would this be? Well, first off, you check your functions. Are these ever discontinuous? No denominators. Okay, so no denominators. All right, because it's not rational. But since we have a piecewise, this is where we would have a potential break. That's where we look. Look at those numbers. Wherever that is, all right, look at that value, all right? And what you want to do is figure out, okay, what is, this is continuity, what is the limit, essentially, when x approaches 1 to the right of this function f, and we also want to compare what happens to the limit as x approaches 1 to the left of f of x, all right? We're going to check this out. So to the right, that's going to be all values that are greater than 1. So essentially, I'm plugging in there. So I'm going to have 1 squared, which equals 1. Right here, I'm going to have this one, which is going to be all values less than that. It's going to be 1. Well, you notice that these are both equal. If they're both equal, then we know that it's continuous. All right, it's continuous because we also know that f of 1 would be plugged into here, which also equals 1. And therefore, this is continuous. So is there any values that are not continuous? The answer is there is none. So which is discontinuities? Well, there is no discontinuity, so there is none. It's because it's continuous everywhere. And so where is this function continuous? It's continuous from negative infinity to infinity. And that's what we get. All right. Well, we're going to stop there and pick it up with some other problems. But we talked about continuity, and we're going to plot this to other problems in a bit.